Evet, merhabalar. Ee, Yavaş yavaş katılımlar başladı. Ben de kısa bir girizgah yaparak bugünkü webinar içeriğimizden, firmamızdan ve kendimden kısaca bahsetmek istiyorum. Akabinde diğer katılımcılarımız da gelecektir ve sözü sunucularımıza ileteceğim. Öncelikle kendimi tanıtayım. Katılımcı listesine baktığım zaman bir saniye, seste bir problem mi var?
Şu an
Düzelttim.
duyabiliyoruz. Bir sıkıntı
Tamam,
yok,
tamamdır.
ulaştık.
Bir uyarı geldi de. Tamamdır. Öncelikle kendimi tanıtayım. Ben Ulaş Taç, BİAS Mühendislik'te veri toplama sistemleri takım lideri olarak çalışıyorum. Bugün beraber webinarını gerçekleştirecek olduğumuz IMC firmasının BİAS Mühendislik'te satış ve uygulama kısımlarından sorumluyum. Satış ve satış sonrası ekiplerimizle de destek sağlıyoruz. Ekibimiz çalışma arkadaşlarımla beraber. Öncelikle katılım ve bu webinarımıza göstermiş olduğunuz ilgi için çok teşekkür ederiz. Farklı sektörlerden mevcut IMC kullanıcılarının da ilgi gösterdiği ya da ilgilenen kişilerin de katılım gösterdiği bir içerik oldu bizim için. İlginiz için teşekkür ederiz. IMC firması aranızda bazıları biliyor ama ondan bahsedeyim kısaca. IMC firmasıyla biz uzun yıllardır çalışıyoruz. Türkiye'de oldukça fazla saygın referanslarımız var. IMC firması sadece telemetri sistemleri değil, aynı zamanda bağlantılı olarak veri toplama sistemleri ve özel sensörler üreten bir firma. Sunum başladığı zaman sunucularda IMC'nin diğer çalışma alanlarından bahsedecek. Ben çok fazla zaman almak istemiyorum, bu anlamda zamanımız limitli. E, ee, Bu IMC firmasıyla düzenlediğimiz ilk webinar. Daha öncesinde farklı partner olduğumuz, beraber çalıştığımız firmalarla beraber webinarlarda düzenledik. Bu IMC firmasıyla beraber düzenlediğimiz ilk webinar ama çok güzel, iyi bir ilgiyle karşılaştık. Bundan sonraki içeriklerimizi de sizlerden gelecek talepler doğrultusunda belirliyor olacağız. Sizlerin bize iletmiş olduğu talepler, görüşmelerimiz neticesinde güncel konulara bakarak neler konusunda hangi alanlarda yardımcı olabileceğimizi belirledikten sonra bu webinar içeriklerimizi yurt dışındaki temsilcisi olduğumuz firmalarla beraber belirleyip sizlere yardımcı olmaya çalışıyoruz. Umarım herkes için faydalı bir webinar olur. Webinarımızın sonunda bir soru cevap kısmı da olacak. Yaklaşık 15-20 dakikalık bir kısımda sorularınızı cevaplamak için bir zamanımız olacak. Bu sorularınızı sunum esnasında sohbet kısmına yazabilirsiniz. Ya da söz hakkı isterseniz ben sizin mikrofonlarınızı açayım ve sorularınızı direkt sunuculara da sorabilirsiniz. Webinar içeriğinde soramadığınız sorular olursa da sonrasında tabii ki bizlerle her zaman iletişime geçebilirsiniz. Bizlerin yeterli olmadığı noktalarda tekrar üretici firmamıza görüşerek sizlere yardımcı olmaya çalışırız. Şimdi sözü ben sunucularımıza devredeceğim. Now we should switch to English now. And Ian and Gergely attend to webinar from IMC company today for us. I would like to introduce both of them quickly to you. Gerge is a area sales manager and responsible for Turkey. Ian is a technical manager in IMC Global Technical Support Team. I would like to thank you, Ian and Gergely, in your presence for their time and support for this training webinar, especially for Turkey. And as we mentioned in our announcements, Ian will be our presenter today. He will share over 40 years of experience in that test and measurement, covering both the fundamental of telemetry and real-world applications today with us. Of course, we will have a limited time today, but Ian has a very comprehensive presentation to share his experience in today with us as much as possible, of course. And as I said, as I mentioned before, we will have a question and answer part end of the webinar. You can write your questions to chat part and we can answer them end of the webinar. So we have a limited time, and now I would like to give the floor to Ian and for his presentation. Ian, you can share your display and take the management, and we can start.
Okay, good afternoon, everyone. Hopefully my screen is sharing now, and hopefully you can all see an Axiometric Solutions logo.
Yes, we can see.
That's excellent, great. The technology works. Okay, so today we're obviously going to be talking about digital telemetry systems. The tagline there about data acquisition from rotating systems is usually accurate. That's the vast majority of what we do is from rotating systems, but any system that is in movement and it's difficult or impossible to get wiring to, so that can also stretch to components that move, maybe conveyor belts or tracks on tracked vehicles, for example. It doesn't necessarily have to be a pure rotation. Okay, just before we start, as Bullosh mentioned in the introduction there, my name's Ian Godwin. I'm the Regional Technical Manager for Axiometric Solutions covering Europe. The 40 years experience has been based quite a lot in, or early years was in the process industries with food and fine chemicals, mixing, blending, that kind of thing. But my life changed a little bit when I left there and moved to a company I'm sure some of you are familiar with, JCB. And the work there, based in the structures department, working on off-highway vehicles, was a bit of a change of direction, using all the same sensors I'd been using, but in a very different way. And that's led really to a sort of a career really based around endurance and durability, noise and vibration, and in particular, an emphasis on how to analyze that data using the tools that are available to us and automate it as much as possible to try and streamline the process to get actionable information as fast as possible and reduce errors. Okay, as I said, I now work for Axiometric Solutions, and we're a group of 3 companies really: Audio Precision, AP, IMC, Test and Measurement, and Grass, the microphone manufacturer. And we've come together really with a shared goal of measuring things in the real world, using the hardware and software then to record that data and analyze that data, and then to try and produce some insights, analyze that data to produce information from all of that data. And we cover quite a wide range. The audio precision side is mainly consumer electronics and audiology, headset testing, that kind of thing. And IMC tends to be more on the industrial test side, so automotive, rail, aerospace, physical testing of components. And Grass obviously sit in the middle, providing the microphone sensors, both to us as companies, but also to anyone who needs microphone technology. The core of it really is, yes, we can provide you with the products, but we're really here to help you solve challenges. So you can buy the equipment straight off the shelf, but we are happiest really when we're involved with you solving problems. From an IMC perspective, we do that with a range of data acquisition systems, all standard products, all that will work well together, so you can combine them to create bigger measurement systems. We have 2 core software products called IMC Studio for running or managing tests and configuring the devices, and a product called Famos for doing the data analysis and producing reports. And as I say, we can sell you the discrete products, or we can get involved and we can create custom applications for you. In addition to those, today we're going to be talking about telemetry systems, in particular digital telemetry, and they sort of sit alongside the data acquisition products. So as well as all the traditional analog sensors, like voltages and currents and strain gauges, we can also add this telemetry data, and we can integrate it direct into the loggers. So everything is available in one place on a common time base in a common file format, so that you can directly compare or directly analyze the telemetry signals alongside the traditional wired sensors. I guess that leaves us with two questions, really. One, what is telemetry? And then the second one leading from that, why digital telemetry? What makes the digital side so special? So starting at the beginning, I guess that most of you are familiar with this sort of standard telemetry application where we have a rotating device of some kind, and we want to maybe measure the torque in that cardan shaft. And it obviously presents some problems. One, it's continually rotating. We can't attach wires to anything. In the past, we may have considered slip rings, but they're not always appropriate. You usually need access to the end of the shaft in order to attach the slip ring device. And although they're better today than they maybe were in the past, they're still prone to problems because you've got these rotating slipping contacts, and particular with things like strain gauges where contact resistance can make a huge difference. Slip rings are not always an appropriate solution, and obviously in this case we can't get on the end of the shaft anyway, so that's a problem. The other issue is these prop shafts tend not to just rotate in a nice fixed geometry. So one end may move relative to the other. The length of the cardan shaft may change on its spline coupling in the center there. And again, that poses us problems if we're trying to get wiring to a common point. And we've also got the universal joints to navigate. The last point to make there is that in some cases it's possible to break into that mechanical system and insert an off-the-shelf torque transducer. So sometimes that is possible, maybe in a test rig, but particularly in a larger in a vehicle test, for example, or marine testing of drive shafts, wind turbines, the option to break into that connection and add an extra component is not always possible. So we have to instrument the components that we've got. So a typical installation might look something like this image here, where we've got the cardan shaft running across there. The telemetry is housed in this black unit clamped around the shaft, and it's got an induction power system, which we'll cover later, which is the copper ring that you can see, and that is supplying the power to the system in this case. So the cardan shaft is free to oscillate up and down, and it will stay within that oval envelope, so we will maintain the power. And in this case, the data signal is transmitted off by radio. So there's an antenna that's out of view at the moment, but we can transmit that data maybe 5 or 10 meters to a receiving antenna. So we get around all of those traditional problems that we've just mentioned. So what is the core sort of components of the telemetry system, if you like? So we need some way to get this measured data off the shaft in a non-contact way, and we're interested in that data in real time. So we can't record it on the shaft and then download it later. We're interested in in seeing that as the thing actually rotates in real time. The two ways, or the two most common ways of getting the data off the shaft are induction systems, which is the one that's shown here, which typically requires that the shaft is well restrained because the non-contact gap that I don't know if you can just make out there is typically somewhere between 5 and 30 millimeters between the fixed pickup and the rotating coil on the shaft. So obviously you need to maintain the stability of rotation of that shaft in order to maintain that distance. Some typically strain gauges or thermocouples will have been attached to the rotating component. We'll have some kind of electronic transmitter device on the shaft, and in this case it's both receiving its power from the induction coil and it's receiving its power from the induction coil, and it's also transmitting its data backward over the coil as well. If we have problems there where this system won't be able to maintain that 5 to 35 millimeters diameter, let me move that out of the way, sorry, then it may be more beneficial maybe to use a radio system to transmit the data, where we've got the same strain gauges on the shaft. Maybe we've got the transmitter, a DX transmitter in this case, on the shaft, and it can transmit its data much further than that 35 millimeters, so typically up to about 10 meters off the shaft, where we can then have the receiver or the receiving antennas mounted somewhere more safely, more securely, and we can receive that data and forward it on for processing. This is the kind of telemetry that we're going to talk about for the remainder of this session today. There are a couple of other definitions of telemetry that we also support, and one of those might be the very long range telemetry that you might see in maybe aerospace situations, where rather than transmitting this data only for maybe 10 meters, we want to transmit data off the aircraft maybe 50 kilometers away. That's a very different kind of solution, which we're happy to talk to you about. We have solutions for that, but they're not the subject of today. The other element is what I would call really telematics rather than telemetry, where you might take that data, you might process it on the vehicle, and then you might upload that data to a cloud server, for example, or email it somewhere. And again, that's a different technology. Again, we do support it, but it's something a little bit different. You've already done the analysis and you're sending analyzed data usually. You're not trying to send usually real-time data. Okay, but why digital telemetry? Before the sort of the mass rise of digital systems, these telemetry systems did exist previously, and usually they were the more close coupled inductive systems that I mentioned earlier on. And typically they used a data transmission method called frequency modulation. So the way that would tend to work would the electronics would generate a fixed frequency, a carrier frequency, which is the waveform shown in green on the screen. And then as the true analog signal came in, the red trace on this display, the signal trace would modulate or alter the carrier frequency's frequency. So in the bottom trace there, hopefully you can make out that as the amplitude of the red signal rises and goes positive, then the frequency increases. We get more cycles per second. as the signal goes positive. As the signal drops and becomes negative, we then reduce the frequency. We expand the distance between the waveform peaks. And then obviously as we go positive again, we compress that waveform up, we get higher frequency again. At the receiving end, we can then decode that in effect by just counting the number of cycles that we get in over a given period. And where we get higher frequency, we can generate a higher output. Where we get a lower frequency, we can generate a negative output. And that worked very well for the time, but it wasn't very good if you're in a noisy environment. And for those of you who've been in this occupation for a while, it's very, very rare that you get nice, clean signals. There's always some kind of noise associated with those signals. And the problem with the frequency modulation, hopefully shown on the right-hand side of the display, is where you get a burst of interference. So this might be some switch gear switching on, or it might be a big electric motor starting. All of these things can generate big pulses of electromagnetic interference. But if they're in the correct sort of frequency band that we are expecting within our frequency modulated system, the decoder will see those as high amplitude signals. It will decode them as a high amplitude value. And we're a little bit stuck because we can't filter that out. And under normal circumstances, we'd apply some kind of filtering to try and exclude that background noise. But if that's a frequency of interest for us, for a high amplitude signal, then we can't afford to exclude it. So we get problems, particularly with noisy transmissions. If we move over into the digital domain, which is probably where most telemetry systems are these days, then we have a slightly different, or a very different approach to transmitting that data. So the first stage is that we sample the data locally. So the incoming data is we take a reading at a fixed time base and we hold that value. So we've calculated at each of those red dots shown on the waveform there, we've calculated a value using an analog to digital converter. We then encode those numbers into a digital data stream, and the one that's probably most common these days is a system called pulse code modulation. So we encode those values into this series of ones and zeros, and we transmit the ones and zeros across either the induction link or the radio link. At the other end, the decoder can read that data stream, and it can interpret them and recreate the numbers from the waveform. And that becomes obviously very precise then, that the number that we encoded at the start is the number that we decode at the end. The other benefit from a noisy transmission point of view is that hopefully from the trace on the right, you can see that even if the ones and zeros have some noise on them, the frequency of the noise is very different than the frequency of the ones and zeros. So it becomes much easier to filter that data out, or to find methods of excluding that noise data and reconstitute or rebuild an accurate representation of the ones and zeros. So this becomes quite a lot more immune to any external noise problems. The other benefit that we get with digital systems is that because we're sending ones and zeros and we're encoding those into a pattern, it also becomes much easier to encode more than one channel into that data stream. So suddenly the availability of multi-channel telemetry became much more prevalent with the age of digital telemetry, because we can get a lot more data across that data link from many channels. So these days, IMC produces a number of different telemetry solutions, and each one really has its own little niche in the application. So they were all created really for a purpose. And what we need to do is obviously to find a method of deciding which one of these solutions is best for your particular application. In general, the T1 and the TEL1 systems tend or are single channel solutions. So if you're looking for maybe shaft torque or a single temperature maybe somewhere, then we can use those single channel systems. If you have multiple signals that you want to transmit, then the other three systems are multiple channels in various sizes, and then they each have their own benefits, which we'll go through in a second. When you're considering a telemetry solution, the chances are that we're going to ask you maybe 4 fairly basic questions to start this process of deciding which system it is that we want to pursue. So the first couple of questions are, how many channels is it that you want to transmit? Obviously, if it's more than one, then the one channel systems probably are not suitable for you. The DX system is good up to about 24 channels. The CTP systems are good up to about 64 channels. And if it's much higher than that, then our MTP system can go up to about 256 channels onto a single receiver. The other question that's equally important there also is what's your desired sample rate? Is this a fairly slow moving shaft or slow moving application where you only need, a few tens or a few hundred samples per second? Or maybe you're looking for something like torsional vibration or a high frequency type problem associated with the component, in which case, maybe 10, 20, 50, even 100 kilohertz sample rate might be required to capture those frequencies of interest. That's a subject in itself, but many of you are probably aware that really to capture, let's say, a 1 kilohertz frequency of interest, you must be sampling at least twice as fast as that. So you would need to sample at least at 2 kilohertz. But if you want an accurate representation of the amplitude of the signal, then really you want to be looking at maybe 10 times or even 20 times the sampling rate to capture a good representation of your frequency of interest. The next question, once we've decided how many channels and what sample rate, the next question that we'd probably ask you is how far have we got to transmit this data? So we touched on this a little bit earlier, that if it's a very well restrained system, maybe a shaft between 2 bearings. So maybe this is something like a wind turbine shaft where the whole system is very well mechanically defined. Then maybe we can go with an induction system with the induction heads quite close by. Maybe it's something where underneath a vehicle, for example, where it's difficult from a packaging point of view to get something very close to a prop shaft or a drive shaft. And also maybe it's got to go through suspension or articulation. So we need to be a little bit further or transmit the data a little bit further than 50 millimeters. So maybe something like the DX transmitter at 10 meters, or the radio systems for MTP and CTP come to play. Maybe we need to go a little bit further. The other one, the CTP8 rotate system that's on the end there is, again, it's a radio system predominantly. But the main reason that exists is for things like aircraft propellers and helicopter rotors, where it's difficult, really. We'll see some application photos later on, but it's difficult to get the receiving antennas in a position, on the right side of the rotors, and it's more beneficial if we can increase that range a little bit to get the signal to be transmitted back inside the aircraft, in order that we can receive it that little bit further away and make the installation somewhat easier to achieve. The other question we'll probably ask you is how should we power this device? So the two choices really are either a self-contained battery system. So in the half shell design on the left there, you can see those pink or purple coloured batteries. So that's a clamshell design that is a standard product for us, where if you can tell us reasonably accurate what your shaft diameter is, then we can provide a system that clamps around the shaft and is battery powered. And the connector on the end here is both the charging port, and if you put a plug in there, it's also the on-off switch as well. And systems like that can run for maybe 4 to 10 hours, depending on what's connected to them. So if going for a day's testing and avoiding all the extra installation challenges of getting an induction system wired up, if you can cope with either charging or changing batteries, then a battery solution might be useful for you. The induction systems, because they obviously you put the power onto the induction system and the telemetry is then powered up. It doesn't need to be rotating. It will stay powered even if it's not rotating, and it means that you can run continuously, day after day after day, with little or no maintenance, and it's ideal for test rigs where you turn the power onto the test rigs and the system is immediately in operation and immediately sending data to you. The last question is really to do with speed of rotation. Most of the systems that we tend to get involved with, or certainly up till relatively recently, I guess, were typically automotive and marine type drive shaft environments, or wind turbine or railway drive shafts. And the speeds of rotation there weren't, they're, maybe, 2,500 RPM is maybe, typical in that kind of application, maybe up to, 3, maybe even 5,000 RPM in certain applications. But the systems can cope with that reasonably well. The enemy here is the centrifugal force, trying to throw even relatively lightweight components, trying to throw them physically off the shaft, or creating such a problem that the shaft goes out of balance because of the instrumentation that we've attached to it. So in the diagram there, you can see that our little T1 transmitter, the blue square, has got a certain mass. It's obviously rotating at a reasonable speed, and a force is there being generated as this little mass rotates with the shaft. The key thing to bear in mind there is the omega squared function. So we've got the mass of the component times omega squared, the angular velocity squared, times the radius from the center of the mass. And that squared is the killer, that if we double the angular velocity, then we affect the actual force by a factor of 4. If we go to 4 times the angular velocity, then we're 16. It's one of these exponential power functions. So in today's applications, where we have things like electric motors in the automotive industry spinning at 20,000 RPM, then suddenly even very, very small attached masses can have a huge force associated with them, trying to either destroy them or throw them off the shaft or destroy the component itself. We'll come to that a little bit in one of the 2 of the applications later on. But in some of those high-speed applications, we also do a version of the telemetry systems that, rather than being discrete components soldered to a circuit board, they're actually connected to a flexible membrane. So the mass of the components of the telemetry system are then distributed around the shaft, and there's no metallic case to take into account. So we try to get the weight down as much as possible and distribute that around the shaft and keep it a very, very low profile so as not to increase that radius very much. So once we've answered those questions, then we're pretty well ready to proceed with the application. I've got a few slides now where we talk about various applications, just to give you an idea of the kinds of things that can be achieved. As I say, a lot of these you will see are variations on the rotating shaft, but then there are some sort of notable exceptions to that. So I guess starting working around, so at the top there, the green image is a typical back-to-back gearbox test, where you use the output from one gearbox to drive another one and then link them together. And you want to know what torque has been generated during that process. So here we've got you can see in the center there a small collar added to one of the drive shafts with the antennas and the telemetry system, and an inductive pickup adjacent to it. The forces in the water turbine, we've got the telemetry equipment. I don't know if you can see, just right in the center there of the turbine. And if you can just make out on the left and the right, there are some antennas there, maybe I would guess around about 0.5 meter away from the telemetry kit, to receive that radio transmission from the water turbine. Oops, sorry. Another big application for the telemetry system is forces on wheel rail sets. This is more of a test bench type setup, the one that you can see on the bottom row there. We also do quite a lot that I mentioned on a different slide, where we're measuring the wheel forces or the wheel stresses during train running operations. The wheel operation there is a stress test on a tire assembly. And what we're interested there is keeping an eye on the actual temperature of the tire assembly while it's rotating. Obviously, the tire is brought into contact with that big metal spinning drum adjacent to it, and spun up to high speed, and it can create quite a lot of heat in the rubber. So it's not just strain gauges and load cells that we can condition. There are other sensor types as well. For off-highway vehicles, so we do quite a lot with in the agricultural and construction sector. So here for class, we monitored the stress in a power takeoff shaft. So the mechanical drive that drives the actual machinery within it's a combine of some kind. So the shaft that drives all the mechanical part of the device. We're measuring the input shaft power there. Obviously, at the bottom corner, a big dump truck measuring the prop shaft to the rear axle. And in the tracked vehicle there, you maybe just make out that on the drive sprocket, we're measuring force or measuring torque on the main drive sprocket on both sides. Of course, there's then different scales. It's exactly the same technology, only the scale changes. So an idea of a big induction ring there for a wind turbine main shaft, and the picture adjacent showing with it installed on the part of the drive gear. There's a lot, not only of main shaft torque, but also when you consider how much mass is cantilevered out of the last bearing on a wind turbine. You know, you've got the hub, the blades themselves, and all the control gear for the blades. Usually people are wanting to measure the bending moments after the last bearing as well, to make sure that the shaft is stiff enough and strong enough to survive that huge bending moment on the end of the shaft. Similar kind of scale are things like marine drive shafts. So we've done quite a lot of work with DEME in Belgium. They do these custom ships for doing cutting and dredging and cable laying. So in this instance, they were interested in the torque. This drop down section of the ship at the back there is actually has a big cutting wheel on the end of it, and the drive for that, the shaft is something maybe like 1.5 meters diameter, maybe with about 50 or 60,000 kilonewton meters running through it. So obviously they want to keep a fair eye on how that's performing, and also things like main shaft, main propeller shaft drives, and other drive systems around the ship. There's a lot of gantry cranes and the support piles and things like that on these big ships, and they want to keep an eye on what's happening with those. From an aviation standpoint, this is where the CTP system tends to be a big favorite. So obviously there we've got the CTP device on the end of a twin prop propeller on the front end of an engine. Also for main rotor and tail rotor, the CTP system can then sit on top of the rotor head and transmit its data back down into the fuselage. And also tire and brake testing on aircraft as well, that obviously particularly during landing, where you've got these huge forces through the brake system and the wheels and tires, and huge temperature rises, then it's interesting to be able to measure that accurately and reliably. So yeah, just another example of helicopter installation on that main rotor. The other, as well as measuring on this image on the right hand side, you can maybe see down at the bottom of the rotor, you can see some orange tape, orange discoloration, which is where the main shaft torque and maybe bending are being measured. But then you can also see these cables running out into the rotors themselves. So in addition to rotor torque, we're also measuring strain gauges to keep an eye on the stress or temperatures of blades as the thing is in the air. Similar kind of idea, but this time on a turboprop engine. So again, we're looking at the blade stress in this case, and because of the number of channels that the customer wanted to use, we couldn't use the CTP system on this. We needed a higher channel count, a higher channel density. So a custom collar was made to fit the MTP system. So each of these modules is 4 channels, and there's a double ring around there, and they sit within here, and the coils for the induction power and getting the data off actually feed back through the hub, and the receiving antennas are built into the engine cowling. So they were laminated into the inside of the engine cowling. As I mentioned earlier, turning railway vehicles or measuring the stresses, bending stresses and vertical stresses on railway vehicles is very important, and requires something like 32 strain gauges per wheel. So in this case, the strain gauges are applied on both the inside and the outside edge of the wheels. You can see the green protective covering there around the wheel sets. And then the data is fed through the wheels, and inside these white discs that you can see mounted on the axle is all of the telemetry components for signal conditioning and transmission of that data. And if you can imagine, this is steel wheels on a steel track, the vibration envelope that this is operating in is quite alarming. You know, there is no suspension here. It's metal on metal contact, and the vibration levels can be very, very high. In a similar vein, we also have put telemetry on mining vehicles, the mining vehicles that cut rock. Unfortunately, due to confidentiality agreements, I can't show you any pictures of those, but you can imagine maybe the cone cutters with the teeth on that grind into the rock and cut it. We've put telemetry on those teeth and also on the main shafts for those cutting mushrooms, and got successful data with the DX system from those. And from the very big, I guess, down to the very small. So things like machine tool monitoring. So we can put the telemetry in to measure cutting tool temperature, cutting tool stresses, for example, on lathes and mills, drills. We can oops, I'm trying to think what that one is. But this is on a vibration compactor piece of construction equipment. Again, you know, the whole purpose of this really is that the wheel itself is vibrating and thumping the ground to compact it as it's rotating. So we're measuring stresses and strains and temperatures within that wheel assembly. Another large drive turbine, I think, on a big rotary mill. In addition, I just spent a couple of minutes that they are sort of more customer specific custom applications where either you, the customer, or us as a service can apply those strain gauges and come up with a customized solution very much for your application. But we also have a range of products where we've pre-packaged the devices for use in a number of relatively standard applications. So things like the DX speed and DX brake temperature are designed to be very quickly and very easily mounted to existing wheels or any rotating structure really where you can get at the center of rotation. So certainly when we put this on a vehicle, within 10 or 15 minutes, everything is in and installed, and we can start collecting data. And again, with the batteries internal, we just plug the connector in, the thing comes alive and starts transmitting, and you can easily get a day or 2 days operation out of a set of batteries. And it's got a sensor in there that's measuring the speed of rotation. Cover a bit more detail in a second. Well, likewise, we can modify that so it can take thermocouple inputs or strain gauge inputs in addition to the rotation. So if you're doing a brake test temperature for a brake temp test, for example, then we can feed those thermocouple cables through to the brake disc through the wheel, and very quickly you can be measuring direct temperatures at the brake disc as the thing is rotating, as the thing is braking, rather than any of the sort of post tests. You quite often see people doing a brake test where immediately the car has stopped, then people are running out with thermal cameras trying to assess what temperature the discs are at, but there's no need for that with telemetry. And the half shell system that we mentioned earlier on, where we can just clamp that around a shaft, connect it to the strain gauges. In this case, we would need to apply some strain gauges to the shaft, but then all of the packaging of the telemetry and the batteries is already done for you. That's come to its own really with the advent of, or the added interest in electric vehicles. Obviously, the particular things like where is the power from the battery system or the electric motor system going? How is it being shared, particularly when you've got one motor driving multiple wheels? And also under the energy, on the regeneration phase, what kind of torques, what kind of energy is being mechanically recovered, and how efficiently are we putting that back into the batteries? So the renewed interest in electric vehicles has obviously seen a much higher, much more renewed interest in measurement on half shafts and drive shafts, particularly in vehicles. And because in this case we can measure the torque on the shaft, but in the bottom left-hand corner there you can see this little extra semicircular circuit board which is doing the speed of rotation, then we can do a direct calculation on the module. If we know the speed of rotation and we know the torque, then we can do a direct measurement of the power. One last application, and then I think we'll probably hand over to questions, is in the electric motor world, keeping an eye on the temperature of your magnets is vital. That if those magnets get too hot and demagnetize, then you're in deep trouble with your motor technology. So we were asked by one of our customers if we could come up with a system, a telemetry system for measuring the temperature, the internal temperature of the motor, directly in the magnetic field itself, obviously, with a temperature up to maybe about 110 degrees. But this motor is spinning at 20,000 RPM. It seemed like an impossible challenge almost, but the guys in the telemetry department in Munich came up with a way of packaging the standard, taking the standard DX transmitter out of its case, but then repackaging it in a custom designed housing where they could get 3 transmitter modules into that housing, and they could do between, well, in this example 9, but in a different example up to 12 thermocouple channels monitored directly inside the motor while it's spinning up at 20,000 RPM. And that's been working reliably now for 12 months or more. And based on the success of the first device, the customers come back and they've equipped all of their motor test benches with that device to keep an eye on the internal temperatures while the tests are being performed. I think I've got one last slide on the flex module, but we've already talked about that. So we'll leave that one be, other than to say that it's good up to about 125 degrees C and around about 10,000 RPM as a standard installation. But it does depend on the diameter. The smaller the diameter, the faster it can go. Okay. So with that, really, that's the end of what I wanted to talk about, and perhaps we can open the floor to any questions that may have arisen.
Yes, yeah, thank you for your informative and instructive presentation, especially to having application notes from several sectors. It was very informative. Thank you. And we have two questions for now. Can you see that?
There we go. There we go.
Yes, we can start with a Barkın-based question, if you can see.
Yeah. So the first question, how do you balance the tested product? Is the center of gravity of your device aligned with the geometric center? And do you use any counterweights or balance weights during the operation? The answer to that really is it depends on the application, which I know is a bit of a cheat. We do provide for the modular systems like the MTP system, where it consists of multiple modules. We do go out of our way to make sure that all of those modules, regardless of what function they have, so some of them are power supply modules, some of them are controllers, some of them are signal conditioners for various sensor types. We do make a very conscious effort to make sure that all of the modules are exactly the same weight, so that then on those modular systems, if you distribute those around the application, so I can just go back to one of the slides we had up. So not that one. Sorry, make everybody dizzy. So this in particular, you can see that these are all regularly spaced around that circumference, and each one is ideally exactly the same mass. In this particular application, because of the nature of it, the whole assembly, once it was completed with the transmitters, the wiring and everything, that was sent away as a complete assembly to be formally balanced. So there was an area on the back of it where we could either drill holes in effect to reduce or affect the balance of the system. In a similar way, for the high-speed motor telemetry in the last slides. Move that out of the way again. If you can see this ring of holes around the back there, they are areas where we designed that specifically so that we could either insert balance masses or maybe drill out the holes a little bit to reduce the mass, because this was going so fast, 20,000 RPM. Even this is maybe 65 millimeter diameter, something like that. But at those speeds, it's critical that the thing is properly balanced. So, yeah, we take care where possible to make the equipment balanced, and then particularly in the high speed applications, we go that extra mile to get physically balanced as well. For low speed applications where we may be putting the DX transmitter on the side of a shaft, so maybe up to, I don't know, I would say maybe up to 1,000 RPM, something like that, you probably don't need to worry too much. And the products are relatively lightweight and are not going to cause too much of a problem. As you go from maybe 1,000 RPM to 3,000 RPM, then yeah, probably we need to be thinking about adding some balance mass on the opposite side of the shaft, or in the case maybe where we're battery powered, maybe sharing that battery load around the shaft as well to distribute the mass a little bit. Okay, hopefully that helps.
Yes, we can go with another one.
Okay, the other question: in hermetic reciprocating compressor experiments, what telemetry-based methods would you recommend to measure suction and or discharge valve displacement. Considering the challenges of oil splash, high frequency motion, and inaccessible geometry inside the cylinder head. The environment is probably key there. I can't say that, I'm trying to think if I've ever been personally involved in that specific application. The nearest I think I can get to that kind of environment is in off-highway experience. We quite often want to measure the torque transfer from the engine through the flywheel and flex plate into either a gearbox or into a hydraulic pump. So typically they are very warm, very high vibration, and quite often there's quite a lot of oil splash in that environment. The other biggest problem that I guess this application would share with that is with all of these, there's a lot of steel or iron, ferrous content in the local vicinity, and that loves to absorb radio waves. So we have to take care to there's a material called mu metal, and we have to take care to shield the surrounding metallic or ferrous spaces with this mu metal to try and to keep the radio signals where we want them. So we've got methods for maintaining the radio. We've got oil splash isn't such a problem. Total oil immersion or total water immersion tends to be a problem. Radio waves don't travel very well through liquids. So oil splash isn't too much of a problem. The last challenge that you've got there really is the hermetic sealing. That somehow, particularly if this is a closed metallic environment, somehow we've got to get those radio waves out. So somehow we've either got to introduce a radio transparent window in the system. So that obviously depends on the application. In some applications, you just physically won't be able to do that. Or potentially we need to find some way of either making the receiving antennas protrude through the outer case and sealing the point where the antennas protrude through, or we need to find a way of, we have remote antennas. So if we can get the remote antennas inside the hermetic environment, then we need some way, a gland plate or something similar, to get the cable, the radio or the coax cables back out of the hermetic environment.
Yeah.
That on the face of it, that does look quite challenging. You know, it's quite a serious application, but there ought to be ways of solving it.
Yeah, environmental conditions an issue is always considered in telemetry applications. And Barkın Bey, if you wish, we can discuss about your application details after the webinar, and we are trying to create an optional ways to help you. Thank you for your question. We have also another question, Ian, on the chat part, not in a question and A, from Kaan Bey. Did you see?
I can only see
not in a Q&A part. It's in a chat part.
Oh, it's in the general chat. 1 second. Yeah. Oh, there we go.
From Kaan Bey. About balancing.
Ooh, yeah, I mean that they're always a balancing after we've installed. but typically they're going to be external methods. I'm just trying to think if we've ever needed to. The only place I've ever really come across that, and it wasn't really to do with the instrumentation in the application of the telemetry. It was a marine application on a ship prop where the telemetry is almost insignificant into the installation compared with the mass of the prop itself. But there was a lot of work done on alignment of the bearings of the prop to make sure that it rotated properly. So there are technologies around there, maybe looking at the vibration or laser vibrometry, that kind of thing, to try and assess the level. Usually, if it's out of balance, you're going to create some kind of additional external vibration somewhere. So there's a possibility to analyze the effects of that. But it can be tricky. The comment that's appeared there is we can verify the balance condition of the shaft by monitoring its vibration levels after the telemetry has been installed, in particular checking the amplitude of the fundamental rotational frequency. That's exactly it, and comparing against acceptable criteria. Yeah, exactly that.
Yes, thank you. And Enes Bey requested a presentation from Mark. We will share with you webinar recording in soon. If you would like to get a presentation too, please contact with me. No problem, we can share if you wish. And is there any other question? Let me check. No, it seems there is no anymore for now. As I said before, when you have a question, you can contact with us whenever you want. If there is no question, we can finish. Yeah. Thank you for all for your part.
I think somebody just jumped in, Ulash, with I have one.
Okay. Yes, there is a new one. Yeah, from Utkucan Bey.
Yeah. Q&A. Sorry, yeah, we're jumping back to the Q&A session.
Okay.
Let's have a quick look. Yeah, so this is a question of about distortion of the signals when using the digital acquisition systems compared to analog. However, I assume occasional distortions may still occur, and in such cases, do you implement any filtering methods? Or do you perform data clearing or data cleaning during analysis stages? The answer to that is probably yes, both. Certainly in the decoding phase of the digital signal to get from the ones and zeros back to real world values, that decoding of the digital system certainly has methods in there to clean up the incoming data, the ones and zeros data stream, in order to effectively decode it. It's also possible to build into that process some error checking to make sure there are redundant bits in there, so that you can check, is the message I've decoded the same one that was originally sent, and then you can decide if for some reason the message was so distorted that you haven't recovered it properly, then you can choose what to do with that data. And it might be that you you reject that packet of information and wait for the next good one, for example. So the digital part of it is certainly cleaned, error checked before it's decoded back into real world values. Once you've got those real world values, there's still the possibility that although we've kept the wiring very, very short from the transducer or the sensor signals, we've kept that wiring very short on the component to the telemetry system. There's still a possibility that in that process maybe some interference has got onto the analog system. So it may be that we've actually encoded some data with some analog noise already built into it. So there's always a possibility, and to be honest, particularly in environments where you've got large electric motors, in a heavy industrial setting maybe, or you need to be a little bit careful in the current electric vehicle world, that suddenly all of our traditional vehicles that were internal combustion engine, and probably the dirtiest electrical system on there was the alternator or the starter motor. Now suddenly you've got a lot of these inverter drives and a lot of high power motors creating a lot of electrical noise within the system. Now the manufacturers of those devices do their best to keep the shielding of the motors and the shielding of the components as effective as possible. But there's still a possibility of seeing some of that electrical noise get into the system before it's encoded, and that's really the place where it's most vulnerable is in those short cable lengths between the sensor and the telemetry transmitter. Once it's been digitized, you are relatively safe. It's highly unlikely the digital data will get noise corruption. It may get interrupted for some reason, but it's unlikely to introduce noise itself. So there are methods then at the analysis point of view where if for some reason you do see spikes in your data or ripple type noise, then there's obviously techniques for removing spikes or removing filtering to remove ripple, or even if you've got a shaft where you're only really interested in the mean torque that it's transmitting, and you've got a little bit of torsional vibration ripple on the top, then it may be that you're quite happy to put that through some kind of low pass filter to get rid of the ripple off the top of the signal and just focus on the mean torque value. And likewise the other way around, it may be that you don't really care about the mean torque, you're only interested in the ripple, so you may be able to analyze it to look at the thing you're particularly interested in and clean that data up appropriately.
Thank you, Ian. And let me check lastly the question part. It seems there is no any other questions. I couldn't be sure, but we can wait if you wish. Yeah. Thank you very much for all for your participants again. As I mentioned in beginning of the webinar, we are open your suggestions and requests and your guidance for the new webinar topics, and we would like to create new contents, new topics for a new webinar series. We are completely open your suggestions, and just let us know for do our best for you. Thanks again for all. Hope to see you again with another webinars.
Yeah.
Bye.
Also, thank you for your attendance. Much appreciated.
Thank you, guys. Bye-bye.
Bye.